It's kind of wild, isn't it, that the tech making games look unbelievably real.
Yeah, the graphics are just stunning these days.
It's also the same engine,
Hmm.
basically, driving huge scientific discoveries and, well, all this AI stuff happening.
It really is a fascinating connection.
Okay, let's try and unpack that today. We're doing a deep dive into NVIDIA's CDA. That's Compute Unified Device Architecture, for anyone wondering.
Right. And our goal here for you listening is really to give you the crucial insights. Where did CUDA come from? How does it actually work, sort of simply put, and why is it such a big deal in computing now?
Exactly. We'll touch on the debates too and, where things might go next.
Yeah, we want to make it understandable, avoid drowning you in jargon.
Definitely. We've looked at NVIDIA's own stuff,
Hmm.
naturally, but also what academics, like folks at Stanford, are saying and how industries are actually using it. So yeah, let's get into it.
Okay.
So first things first, what is CUA? And maybe more importantly, why should you care?
Okay, so fundamentally, CUDA is this parallel computing platform, and it's also an API, an application programming interface. NVIDIA brought it out back in 2006.
2006, wow. Seems like ages ago now in tech terms.
It really does. And its main job, its core function, is to let software use the massive processing power that's sitting there in a graphics processing unit, a GPU.
But not just for graphics, right? That's the key.
Exactly. That's the whole GPGPU idea, general purpose computing on GPUs,
Oh.
using that graphics hardware for, well, all sorts of heavy duty calculations.
So the big shift is, instead of just the CPU doing everything step by step,
Right. CPUs are great at sequential tasks, complex logic, one thing after another, very quickly.
you push the really parallel stuff, the calculations you can do all at once, over to the GPU, which has like thousands of little workers.
That's a great way to put it. Thousands of cores ready to tackle bits of the problem simultaneously. And that's the aha moment. The speed boost you get for computationally intense work is just, well, dramatic.
Okay, I like the analogy. CPU is the master craftsman. GPU is the whole workshop buzzing with activity.
Precisely. For the right kind of job, think huge simulations, massive data analysis, that workshop approach is unbelievably faster. It's really changed how quickly science can happen.
Right, speeding up the whole discovery process.
Absolutely. Stuff that might have taken years of computation can now maybe be done in weeks or months, iterating on ideas so much faster.
Okay, so it lands in 2006. What were some of the big steps, the milestones since then? Hit the highlights for us.
Sure. So 2006 was the start. Then maybe the next really big one was CUDA 2.0 in 2008.
What was special about 2.0?
Well, crucially, it added C++ support. And that was a really big deal.
Ah, because loads of scientists and engineers use C++.
Exactly. Suddenly, this powerful tool became much more accessible to the people who could really use it for complex simulations and modeling. It broadened the whole user base significantly.
Makes sense. What came after that?
Then, 2009, NVIDIA brought out the Tesla architecture. This wasn't just about individual graphics cards anymore. This was specifically designed for data centers.
So targeting the big iron, the large-scale computing places.
Right. You can see the strategy unfolding, not just gamers, but the whole computing infrastructure. Then CUDA 3.0, that introduced dynamic parallelism.
Dynamic parallelism.
Yeah, basically letting tasks running on the GPU launch other tasks on the GPU without needing to go back to the CPU to coordinate everything.
Ooh, okay. Like the GPU managing its own workload more.
Kind of, yeah. More flexibility for really complex parallel problems. Kernels launching other kernels, as they say.
Powerful stuff. What about more recently?
Hmm.
AI seems to be the big driver now.
Definitely. A huge step was CUDA 9 in 2017, which came alongside the Volta architecture.
Mm.
And the big news there was tensor cores.
Tensor cores, I hear that term a lot. What are they, simply?
Think of them as specialized little math engines built right into the GPU. They're incredibly good, incredibly fast at the specific kind of matrix math that, well, powers most of modern deep learning.
Gotcha. So purpose-built hardware for AI calculations.
Exactly. And since then, a lot of the focus has been on making CUD work really well with all the popular AI frameworks, the machine learning languages, and just generally keeping it at the forefront for scientific computing and data analysis right up to today.
Okay, a constant evolution. Let's try and peek under the hood a bit, but, keep it manageable. How does CUDA actually make the GPU do all this work?
The magic is really in harnessing that parallel architecture. GPUs have, like we said, thousands of these smaller cores, way more than a typical CPU. CUD gives developers a way to actually manage all those cores effectively.
How does it manage them? Is it like just telling each core what to do individually?
Not quite individually. GPUs often work using a model called SIMD single instruction, multiple data.
Sí,
I mean,
anyway.
think of it like a drill sergeant shouting one command, and the whole platoon does the same thing at once, but maybe on slightly different data.
Okay, so one instruction, but applied across lots of data points simultaneously.
Exactly. And the way developers tell the GPU what instruction, what work to do, is through the CUD programming model.
Right, the model. What are the key pieces there?
Well, you have things called kernel functions. A kernel is basically the chunk of code, the little program that you want to run in parallel on all those GPU cores.
So the specific job you want done.
Yep. And these kernels are executed by lots and lots of threads. You can think of a thread as one instance of your kernel running.
Okay, thousands of threads running my kernel code. How are they organized?
They get grouped into blocks. So you have threads within a block and then multiple blocks. It helps manage the complexity.
And do threads in a block work together somehow?
They can. That's where shared memory comes in. It's a small amount of really fast memory right there on the GPU chip that threads within the same block can use to share data quickly, much faster than going out to the main GPU memory.
Oh, okay. Like a local scratch pad for the team.
Good analogy, yeah. And to make sure things happen in the right order, especially when they're sharing data, you have synchronization barriers, like waypoints.
Exactly. A barrier says, okay, everyone in this block, finish what you're doing up to this point before anyone moves on. Essential for coordinating complex work.
I've also heard about unified memory. What's that about? Sounds helpful.
It is helpful. Unified memory basically lets the CPU and the GPU see the same memory space, virtually at least.
So they share memory. How does that help?
It simplifies things for the programmer.
Mm-hmm.
You don't have to manually copy data back and forth between the CPU's memory and the GPU's memory quite so much. The system handles more of it automatically.
Less boilerplate code, basically.
Pretty much. It makes development easier and potentially more efficient. It's interesting, AMD has explored similar ideas with their HSA, heterogeneous system architecture. That's a common goal.
And one more hardware trend, chiplets. People are talking about GPUs made of smaller pieces now. How does that fit in?
Chiplets are definitely a big thing.
Mm-hmm.
The idea is instead of making one giant monolithic GPU chip, which gets harder and harder to do well, you build a GPU out of smaller, specialized chiplets all connected together. Sort of like Lego bricks?
Kinda, yeah. It can improve manufacturing yields, let you mix and match different capabilities, and potentially scale performance better. It's one way the industry is trying to keep pushing performance forward as traditional scaling slows down. CGT needs to work efficiently across these kinds of architectures, too.
Okay, that makes sense. So we have this powerful engine, CDA, driving these GPUs. Where are we seeing the biggest impact out in the real world?
Oh, it's really widespread now. Gaming is the obvious one, right? That's where it started for NVIDIA.
Yeah, powering incredible graphics, ray tracing, and all that.
Exactly. Real-time ray tracing, which gives you those super realistic lights and shadows, relies heavily on CDA and the dedicated RT cores on NVIDIA's RTX cards. It makes games look phenomenal.
Definitely seen that leap. But beyond games.
Data science and machine learning are huge. CDA absolutely smashes through the complex math involved in training AI models and analyzing enormous data sets.
Any specific examples?
Well, the outline mentioned retailers like Lowe's using it for optimizing their supply chains. Think about predicting demand, managing inventory across thousands of stores. That's a massive data problem. CUDA helps them crunch those numbers fast.
Right. Real business impact. And scientific research. You mentioned that earlier.
It's been revolutionary there. Things like weather forecasting models are becoming much more accurate because they can run more complex simulations.
Okay.
Fluid dynamics, simulating how air flows over a wing or water through a pipe, and molecular dynamics, simulating how proteins fold or drugs interact with cells. CUDA has brought speedups of like 30 times or more in some cases compared to just using CPUs.
30 times. That's transformative, not just incremental.
It really is. It allows scientists to ask questions they just couldn't computationally afford to ask before.
What about the cloud? All those data centers.
Big impact there, too. NVIDIA introduced tech like MIG multi-instance GPU with their Ampere architecture.
Yeah.
It lets you partition a single big GPU into several smaller, independent, virtual GPUs.
Ah, so one physical card acts like multiple smaller ones.
Exactly. It means data centers can slice up their powerful GPUs and serve more users or different types of workloads more efficiently. Better utilization.
Smart. And the outline also mentioned self-driving cars and content creation.
Yep. Autonomous vehicles need to process insane amounts of data from cameras, radar, LiDAR, all in real time to make driving decisions. CUD provides the processing muscle for that.
High-stakes stuff.
Absolutely. And for video editors, graphic designers, 3D artists, CUDA accelerates rendering, applying effects, all those tasks that used to take forever. It saves massive amounts of time.
Okay, so it's clear CED is more than just, like, one piece of software. It sounds like a whole environment, an ecosystem.
That's the perfect word for it, ecosystem. It's not just the core CD ATI. A huge part is the CED toolkit.
The toolkit.
Yeah, NVIDIA gives this to developers for free. It's got the compiler, the thing that turns your code into instructions, the GPU understands, plus debugging tools, optimization tools, and really importantly, a whole set of libraries.
Libraries for specific tasks.
Right, like you often hear about CUDNN.
Yeah, CUDNN comes up all the time with AI.
It stands for EUD Deep Neural Network Library. It basically provides super optimized building blocks for common deep learning operations. Convolutions, activations, things like that. So developers don't have to reinvent the wheel. They can just use these fast, pre-built components.
Saves a lot of work and gives good performance.
Exactly. And then there's TensorArt.
TensorArt, is that related to Tensor Cores?
It is. TensorArt takes an AI model that you've already trained and optimizes it like crazy for running efficiently in production, what they call inference. It makes the model faster and use less memory when it's actually making predictions.
Okay, so CUDNN helps build and train. TensorArt helps deploy.
That's a good way to think about it. And if you're training really massive models, the ones that need clusters of GPUs.
Which seems increasingly common.
Right. Then you need something like NCCL, the NVIDIA Collective Communications Library. It's all about making multiple GPUs talk to each other really, really fast, essential for large-scale distributed training.
So a whole suite of tools supporting the core CUDA platform.
Yeah, compiler, runtime, libraries, debuggers, profilers. It's a very comprehensive ecosystem.
And you mentioned earlier this gives CUDA a competitive edge.
Often, yes. It's not just raw hardware performance, though that's obviously critical. It's also the maturity of these tools, the documentation, the support, the sheer number of developers familiar with it. Many find it just easier to get high performance out of NVIDIA GPUs using CUDA compared to alternatives.
Which brings us to that recurring point.
Yeah.
The open versus proprietary debate.
Right. It's the elephant in the room, really. CUDA is amazing, powerful, well-supported, but it's NVIDIA's technology. It locks you into their hardware.
Vendor lock-in, the classic trade-off.
Exactly. If you build your entire workflow, your applications around CUDA, moving to a different hardware vendor later becomes, well, difficult, maybe impossible without a major rewrite.
So organizations weigh the immediate performance and ecosystem benefits against that long-term strategic risk.
That's the calculation many have to make. For a lot of cutting-edge research or performance-critical applications, the benefits of CUDA right now are just too compelling to ignore, even with the lock-in concern. But it's definitely something people are very aware of.
So who are the main alternatives? What's the competition look like?
Well, the big one historically has been OpenCL, Open Computing Language.
OpenCL, that sounds open.
It is. It's an open standard managed by the Kronos Group. The big promise is portability. Write your code once. Run it on GPUs from NVIDIA, AMD, Intel, even other types of processors like FPGAs.
That sounds ideal. Why isn't everyone using it then?
The reality has often been more complex. Getting consistently high performance across different vendors' hardware with OpenCL can be challenging. The implementations vary, the tooling hasn't always been as mature or user-friendly as CUDA's, and sometimes the language itself felt a bit, well, lower level or harder to work with, especially in earlier versions.
So portability in theory, but maybe headaches in practice.
Sometimes, yeah, though it's definitely improved over the years. Then you have AMD's main effort, which is ROCm.
ROCm Radeon Open Compute.
Right. This is AMD's open source software platform, specifically for their GPUs. It's gained a lot of traction, especially in high-performance computing circles where open source is highly valued.
How does it stack up against CUDA?
It's getting better and better. AMD is investing heavily. But the perception, generally, is that the ecosystem, the libraries, the tools, the breadth of framework support might still lag a bit behind CUDA's maturity, though that gap seems to be closing.
And there was one more mentioned, UXL, Unified Acceleration Foundation.
Yeah. UXL is newer. It's an industry consortium. Intel, Google, ARM, others are involved, trying to build open standards for accelerator programming, kind of like a next generation attempt at what OpenCL aimed for, maybe learning from past experiences.
So trying to create a more unified, open alternative to CUDA's dominance.
That seems to be the long-term goal, yes. Create a common ground. We'll have to see how that develops.
Okay. Now, despite all its success, CUDA isn't perfect. What are some of the main criticisms or challenges people run into?
Well, one thing relates back to that SIMD model we talked about, single instruction, multiple data.
Right, everyone doing the same thing.
It's most efficient when all the threads running in parallel are actually following the same execution path. But sometimes, depending on the data, threads need to do different things. They diverge.
Like an if statement where some threads go one way, others go another.
Exactly. That's called thread divergence. And it can hurt performance because some threads end up waiting idly while others complete their different path. Complex algorithms like, say, some forms of ray tracing can run into this.
So the architecture has inherent limitations for certain types of problems.
It does, or at least it requires careful programming to work around them efficiently. Another niggle some developers mention is the CUDA compiler, sometimes being a bit too strict, maybe flagging C++ code that should be perfectly valid. That can be frustrating.
Fighting the tools isn't fun. And the vendor lock-in thing, what are the real-world consequences people worry about?
Well, think about cloud computing. A huge amount of AI training and scientific computing happens in the cloud now, and NVIDIA GPUs are, frankly, dominant in that space.
So cloud providers mostly offer NVIDIA.
Overwhelmingly, for high-end GPU compute, yes. Which means if you need that kind of power, you're likely paying for NVIDIA hardware and using CUDA. This concentration gives NVIDIA significant market power, which can impact pricing choices and maybe slows down broader ecosystem innovation if alternatives struggle to compete.
Especially maybe for smaller players, universities, or startups.
Could be, yeah. Access and cost become bigger factors.
You also mentioned OpenCL's API limitations compared to CUDA.
Yeah, historically, OpenCL started with just a C API, while CUDA embraced C++ earlier, which many developers preferred. And often the supporting tools around OpenCL, like good debuggers, profilers integrated into development environments, just felt less polished or comprehensive than the CUDA toolkit, making the day-to-day development experience potentially smoother with CUDA.
Got it. And there was a philosophical point about performance focus.
Yeah, that's a bit more subtle. Because CUDA and GPUs offer such potential for speed up, there can sometimes be a culture of chasing every last drop of performance, focusing intensely on micro-optimizations.
Which sounds good, right?
Yeah.
Faster's better.
It is, but sometimes that intense focus can come at the cost of, say, development time, code complexity, or maintainability. There's a balance to be struck. Is spending an extra week optimizing one small function worth it if the whole project gets delayed? It's about efficient overall development, not just raw execution speed.
A good reminder. Okay, looking forward then, what's the future likely hold for CUDA and this whole field of GPU computing?
Well, one thing's for sure. The need for more performance isn't going away. But the old ways of getting it, making single cores faster and faster, have really hit limits. Dennard scaling, Moore's law, they're slowing down.
So parallelism is the main path forward.
It really seems to be. We need to use more processors working together, and that means GPUs and platforms like CUDA to manage them become even more critical. Plus, there's a huge focus on energy efficiency. You can't just keep throwing power at chips.
Right. Power consumption and heat are massive issues, especially at scale.
Exactly. So expect continued innovation in making parallel processing powerful and power efficient.
So GPU isn't just a phase, it's fundamental now.
Absolutely. This hybrid model CPU for general tasks, GPU for the heavy lifting, the computational hotspots, is pretty much the standard for high-performance computing now and likely for the foreseeable future.
And will the way we program these systems need to change?
Probably. As the hardware gets more complex, think chiplets, tighter CPU-GPU integration. The software tools, the programming models, will need to evolve too. We might need even smarter ways to express parallelism and manage data movement between different types of processors.
Making it easier for developers to actually use all that power effectively.
That's the goal, abstracting away some of the complexity while still providing access to the performance.
Okay, and one last point from the outline. This idea of addressing feature creep. What's the concern there?
It's a common challenge with any successful evolving technology. As CUD adds more and more features, libraries, options, There's a risk that some additions might be more about checking boxes or marketing than providing genuine, significant benefits.
Bloat, basically.
Kind of, yeah. Or just adding complexity without a clear payoff in performance or usability for most people. The challenge is to keep innovating meaningfully, ensuring new features really help solve problems or improve efficiency, rather than just making the platform bigger and more complicated for its own sake.
Maintaining focus on what really matters.
Ex-
Okay, wow, we've covered a lot of ground. Let's try and maybe quickly summarize the key takeaways from this deep dive on CEDA.
Sounds good.
It seems pretty clear CEDA has just fundamentally changed parallel computing. It started in gaming, but now it's indispensable everywhere.
Absolutely. Its evolution, the way it unlocks GPU power for general tasks, its use in AI, science, data centers, it's huge.
And that whole ecosystem around it, the toolkit, CUDA, TensorArt, NCCL, that's a massive part of its strength, right?
Yeah.
Even with the proprietary concerns.
Definitely. The ecosystem is a major advantage. And yeah, the open versus closed debate, the competition with OpenCL and ROCm, those are ongoing, important discussions in the field.
So its impact is undeniable, and it seems like its future, tied to parallel processing and efficiency, is pretty central to where computing is heading.
I think that's fair to say. The hybrid CPU-GPU model driven by platforms like CAD is likely to be key for a long time.
Okay, so for you, the learner, listening to all this, as you think about how CUDA has enabled so much, from, better game graphics to potentially life-saving drug discovery, here's a final thought to chew on.
Yeah.
What does it really mean when one company's specific technology becomes so fundamental, so deeply embedded across so many critical fields? What are the upsides, maybe the efficiencies gained, but also what are the potential downsides or risks of having that much computational power concentrated around one vendor's platform? Something to think about regarding the future shape of innovation.